Welcome to the UEI Technical Masterclass. I hope everyone here is doing well today. I'm Bob Finn with UEI, and today's webinar is entitled OPC-UA in Modbus, Industrial Communication Protocols. As the title suggests, today's session will take a look at Modbus, one of the most popular industrial communication protocols, as well as OPC-UA, a newer protocol with a number of features like support for IoT platforms. Our own Austin Turner will be today's presenter, and backing him up will be our application engineering team, who are always eager to answer any questions you have about today's topics. Got a question? Send it our way using the webinar chat tool, and please don't be shy. So, without further ado, I'll hand this over to Austin.
Thanks, Bob. So my name is Austin Turner, and I'm an application engineer here at UEI. Today we're talking about Modbus TCP and OPC-UA, two of the more popular industrial communication protocols. So let's step into Modbus TCP first. So Modbus has been around for a while. It was developed in 1979 by a company called Modicon, specifically for their PLCs. Prior to having Modbus, there was a need for what we call home run cables, which is a long run of cable from the sensor back to the control room. So when we developed Modbus, it was a way to create a distributed system so that you could have these sensors that talk to, say, a data concentrator. So you have multiple sensors all talking to a single PLC, and then the PLC can talk back to the control room over a few wires. It was the de facto, or actually it is the de facto industrial communication protocol, partially because it's open and it's very, very simple and easy to implement. The main components of Modbus that you'll hear about are the sensors. So that can be the thermocouples, it could be RTDs, it could be pressure transducers, it could be a simple voltage or current, 0 to 20 milliamps, 4 to 20 milliamp signal. These are going to be connected to a remote terminal unit, or RTU, sometimes referred to as a data concentrator. And that's going to be communicating over Modbus back to a computer, which is going to be running your SCADA system, or supervisory control and data acquisition. Within that SCADA system, sometimes you'll have an HMI or a human machine interface, and that's a way to easily consume the data. There's two main types of Modbus. The first is the original Modbus RTU, and that's serial communication. The second is Modbus TCP/IP, which is basically a wrapper around the Modbus RTU, and now uses the Ethernet backbone. So again, the Modbus architecture is extremely simple. We'll take a look at the next slide of the main backbone of Modbus, of how it works, the Modbus registers. So the architecture, though, is a master-slave. Although when we talk about Ethernet and TCP/IP, we typically refer to them as client-server. So the client is synonymous to master, and server is synonymous to slave. The master sends a query or request. The slave waits for the query and sends a response. And the control is always master to slave. The slave is always waiting and really can't do anything without the master sending a request. Because of that architecture, we're limited in the amount of data it can move. So since the master has to always request for data, there's actually a max set of registers it can read or write to as well. So we're not going to have high-speed acquisition or high-speed control. High-speed Modbus would be in the low kilohertz range. And it's non-deterministic, so we don't know exactly, we can send the request, but without an actual timestamp, we don't know exactly when that data was taken. So here's the real crux of Modbus. So it's these Modbus registers that make it up. And we'll start off with the register 0XX, which is for coils. So coils, originally when we talked about when Modbus was developed, we're talking about relays and the actual coils of a relay. So this is going to be reading and writing to a coil of a relay or any discrete output. We follow up with the 1x registers, and that's going to be discrete inputs. So it's read-only, we're not controlling anything, but we're just reading a status on, off. Again, a single bit similar to the coils. The 3x and the 4x registers, those are going to be used for your analog values. So these are 16-bit wide. The 3x is going to be your read-only. And then if you're writing analog values, you're going to use that 4x. So when the master tries to get data or sends a control, it's going to refer to either writing a coil, writing a holding register, or reading one of those registers as well. So from the previous slide, you may be thinking, 16 bits. What can I do with 16 bits nowadays? Well, we can just put together two contiguous registers, and then we get a 32-bit value. So we can do that to represent our 32-bit floating point precision values. Well, what if I need 64-bit? Just as easy. We can now combine 4 registers of the 16 bits to create a 64-bit value. It's worth noting, though, that not all Modbus servers do represent the 32 bits with upper and lower, how I've shown it here, and sometimes it'll actually be swapped. So you'll want to consult with your Modbus device to see how it's sending the data. Another kind of downside about Modbus, though, is there's no identification of what the register contains. So it's just a data stream, and it's just sending a floating point value. Modbus doesn't say this is voltage or this is current. It's up to your application, the Modbus master, to know what the Modbus server is sending, and part of that is user input. So this 16-bit Modbus registers, it really does allow for flexibility at the same time. So we can have Modbus Bridges. So even though Modbus wasn't created with the intention of supporting serial or ARINC 429 or other avionics protocols, it can be implemented by using those registers. So we had a previous masterclass covering the ARINC 429 protocol. I'm not going to go into too much detail here, but the UEI Modbus server, we do support ARINC 429, and this is an example of the input side of ARINC 429. So what we've done is we filter on a specific label, and we'll actually take the data and put it into 2 contiguous registers, low and high. We will store the SSM, the SDI, and then we'll also save a 32-bit timestamp using 2 contiguous registers. So we've already defined the registers for you. It's up to configuring the Modbus master to then read those registers, but now you know what those registers are. So UEI Modbus. We do support Modbus TCP/IP, and we're very flexible. So regardless of which chassis you choose here, whether it's rack, industrial cube, or military chassis, all support the Modbus TCP server, and it's all identical hardware across all platforms. We do have over 30 different I/O boards. So whether you need something for accelerometers, thermocouples, RTDs, we should have that board covered for you. And we're also very rugged. So if you need to cover the extreme temperature range, vibration shock, we have that covered as well. And soon I'll be showing a demo to show how you can use our web configurator so that you can configure the Modbus TCP server without having to write any code. Okay, so let's step into the UEI Modbus demo. So here I've typed in my IP address, and then I follow that up with /modbus.html, and that brings me to the web configuration page. So on the left side, we can see the devices that I have. I have an analog input, DIO, which is actually mechanical relay, analog output, specific analog input boards, so for accelerometer, current, so if you have your 4 to 20 or your 0 to 20 control loops, you're going to use a AI 204. And then specifically a thermocouple board that has a built-in CJC. We can configure the timing, so if we want to have a higher scan rate, we can change that as well. We can save that configuration. We can start the Modbus slave, and we could also check this off so that upon power up, we automatically start the Modbus slave. For now, I'll just start it. Okay, so now the chassis is communicating its data or ready to communicate over Modbus TCP. So to configure the Modbus master, it's good to know which registers we're using. We provide a register map so we know here are the coils we're using. We don't have any discrete inputs. Here are the input registers, and here are the holding registers. All this is documented in our manual showing how we use the registers and the offsets that we use. So for the Modbus master, you can use any open source Modbus master. They're all going to be talking over Modbus, so this should automatically work. There's a lot of different libraries out there as well. So if you want to write your own Modbus master, you can do that. And that's what I've done here. I've written my Modbus client using Python. And I have my loopback test adapter, so we can see I have 7.5 and negative 7.5 volts alternating. I can disconnect. And we have floating values. And reconnect again. And let's just take a look at that Python code. So it's pretty simple. I'm using PyModbus TCP. There's not much to it. I need an IP address, a port. Once I open a handle to the Modbus client, I can open that client, connect to the server, and then run my forever loop to read inputs. If I wanted to read digitals, write coils, I can do all that. The most complicated part was just taking the data, taking two separate registers, combining them, and then converting it to a floating point. Since I'm most familiar with C code, I use the C types library of Python, cast using some pointers to cast the raw value to a floating point value. And that's it for Modbus. So let's look at if any questions have come in. Okay. Is it possible to get high sample rates, say 50 kilohertz through Modbus? Intrinsically through Modbus alone, no. It can't handle that high data rate, especially because you have a master that has to pull the slave. So we've implemented, though, a form of our VMAP API. And for those not familiar with the VMAP API, it's basically a way to sample at a specific data rate and return a buffer of data. So with this custom solution, it was basically a state machine where the Modbus client would control the configuration of the VMAP, when to start the VMAP, how long to run it for, and then it could read the data. And again, we're limited in how many registers we can read at a time. So depending on how much data we had sent, it may be multiple reads. So really the answer to say, can we get 50 kilohertz through Modbus? Yes, but it does take a custom solution to get around the limitation of Modbus. Another question came in. How do I know what data is being read from each register, i.e. engineering units? Unfortunately, you don't. So Modbus doesn't have a way of storing units along with the value. You need to check with your Modbus server and then configure the client based on those values that the server is representing. Okay, is there any security with Modbus? Again, unfortunately, no. There's no security. Modbus is simply a communication protocol at the application level. So it's only defining the bits and what they represent. I will say though, if you have a lot of data flowing over Modbus, it might be difficult for someone to snoop the traffic and decipher what the data is actually being represented. Because again, Modbus doesn't have a way to show engineering values. So someone might see, or someone might be able to decipher that it's 7.5 and negative 7.5 volts, or not even volts, but just those values. But what does that mean? Also, Modbus is typically on a LAN, so it's not going to be connected to the internet. If it was accessible to external devices, you may want some protection for controlling outputs. But again, that's not something that Modbus inherently supports. Hopefully that answers that question for you. Which of your boards are supported through Modbus and OPC-UA? Well, we'll get to OPC-UA, but the answer stands for both of them, that all of our analog and digital I/O boards are supported. I did mention in the slides, we do have an A-Rink 429 over Modbus Bridge. So really anything outside of the typical analog or digital I/O does require some customization, but it's not unfamiliar territory for us. Okay. If there's no more questions for Modbus, let's jump into OPC-UA. So before we get into OPC-UA, it's good to see where it started from. And it started from just OPC. So originally, OPC stood for OLE for process control. So OLE, O-L-E, is a Windows system. It stands for object linking and embedding. Again, it is Windows specific, and it's usually used for linking and embedding documents, exchanging data between different applications. If anybody's familiar with DDE, Dynamic Data Exchange, that's part of the OLE subsystems. So now, though, OPC is known as Open Platform Communications. What it does is it defines objects and methods, and that allows for interoperability. And we'll take a look at that in the next few slides. There's two main forms used with OPC, two main methods. The first is OPC Data Access, or OPC-DA. And again, that's the most common. And that's the way that you're going to, from your OPC client, that's the way you're going to get your data from the OPC server. And we also have OPC Historical Data Access, and that's a way to see a trend of the data over a specific time period. So why is OPC needed? Well, if we take a look at this diagram, we see multiple different hardware, all with their own drivers. And then we have software packages at the top: display application, trend application, report application, which could technically be in one singular software package, but still they all need a way to get the data from the hardware, which means they all need a way to communicate and use that software driver. So we have really an issue here with interoperability because we've had to re-implement the software driver in each of our applications. So that's where OPC comes in. So if we standardize on a format, then any hardware and any software, as long as it's using the OPC standard, can be plugged into this system and work right away. So now we step into OPC-UA. So the UA stands for Unified Architecture. And its aim was taking OPC, but increasing interoperability with a platform agnostic take. So instead of being Windows-based, now it's going to be platform agnostic. So we can use those different flavors of Linux, or possibly some operating system outside of the normal range, maybe Solaris or one of the others. It has better scalability and better performance. So that's part of the enhancements. It added multi-threading, and again, a lot of that is in the background of OPC-UA, but it's going to have better performance than the standard OPC. It offers security. So one of the things about OPC-UA is it targets the IoT world, or Internet of Things. It really needed to have some form of security, authentication, and encryption to make sure the data is safe. There's two protocols for OPC-UA. One is the binary TCP. That's going to be a lightweight form, or lighter weight than the web service, and that's what we support here at UEI. And then there's the web service HTTP. Again, kind of in the name, if you're creating some web service, web page, you're probably going to use that form of OPC-UA. And now we look at the OPC-UA client. So when we think of Modbus, we really had to configure our Modbus master to match what the Modbus server was displaying. So we had to manually input the registers that we're going to read from, and also put in the engineering units. All of that can be done in the background of the OPC-UA client. So once it connects to the OPC-UA server, there's an auto discovery of the server variables and address space. So if we look at the bottom left there, that address space of the UEI devices, they might be a little small on this page, but all of that is read directly from the server. So all you've had to do is implement the server, tell it which devices to use, tell it which channels to use, and the client will automatically discover that address space. So we're cutting down time, and we're cutting down possible issues that could happen when you're trying to configure your Modbus master. OPC is based on tags and nodes. So those are two common terms. We're not using registers anymore. We're using tags and nodes to look at the data. So the benefit of OPC-UA, or at least one of the benefits, is with more adoption, that means more protocols with an OPC-UA bridge. So when you have your software package, it may be able to communicate over Modbus, but then it's going to take that data and it's going to reformat or repackage it into an OPC format. That way it's ready to be distributed to any other system. The high-speed data requires custom solutions. So we can't sample at a high rate, say 50 kilohertz worth of data. We need some way for the client to maybe tell the server to start acquiring high-speed data, and then the server will have to process that, and it'll have to send it over to the client over a longer period of time. And for those not familiar with HMI, I wanted to get a picture of exactly what it looks like. So we're not looking at data in textual format and trying to correlate it to what could be happening within a system. The HMI is creating a very easily consumable way to view the data, so that while you're looking at this value, say 33 PSI, you know exactly what it is corresponding to, compressor 1 in this case. Now, this is just one example of using the Ignition software, but you could use any of those other software packages, whether it's Wonderware, Kep Server, Iconics, OCSoft Pi System, and I'm sure there's a lot more others out there. So here we have the UEI OPC-UA. So similar to Modbus, we're going to configure OPC-UA through a web page, a web configuration. Again, on the hardware side, it's supported throughout our platforms because we use the same hardware throughout all of our chassis. So again, if you need the industrial cube, military chassis, or just a rack, OPC-UA is supported, and again, in those rugged environments as well. So now let's look at an OPC-UA demo.
Oh, hi, I'm Phil, an application engineer here at United Electronic Industries. UEI data acquisition and embedded control products work with a wide variety of software applications, including OPC and OPC-UA. OPC-UA is an industrial machine-to-machine communications protocol designed to act as a cross-platform, service-oriented architecture for process control with enhanced security. When implementing a system using OPC, one has to consider the client side and the server side, or in other words, the UEI equipment side. The OPC-UA server runs on our UEI Programmable Automation Controller, or UEI PAC. OPC-UA client applications can connect to subscribe to labels and retrieve historical data. The OPC labels are associated with physical channels, and you can organize them, i.e. select where the label will be in the OPC address space, in a way that best fits your application. The label association with physical channels, as well as the label location in the address space, can be configured with our UEI Web Configurator. To access the Web Configurator, simply open a browser and type in the IP address of the cube, followed by /UEIOPC.html. Here we configure the cube to the settings of our choice. When naming the channel ID, you can use specific labels to later determine what data you are monitoring. Make sure you enable the channel you would like to monitor, and then select the parameters for that channel. Once you're done, just click Save Configuration, and the configuration file is now stored on the SD card. And the OPC server can then be started. Okay, we've just shown you how to configure the OPC-UA server. Now let's take a look at the client side. You could use existing clients or build your own. Commercial SDKs are available for C, C++, Java, and .NET. Open source SDKs are available for at least C, C++, Java, JavaScript, and Python. Simply drop the channel of interest into the data access view, and you are now reading the data from the server. It's that simple.
Okay, so that ends it for OPC-UA, but now let's look at any final questions that have come in. Okay. What kind of data rates are supported through UEIModbus and UEIOPC? I think a safe bet is 2 kilohertz, although we may be able to run a little bit faster than that in some instances. It really depends on the amount of channels that you need to send. Again, these protocols aren't ideal for high-speed acquisition or control. Instead, if you want high-speed acquisition, you may either choose not to use these protocols. We certainly support high-speed acquisition in different methods using our API, or it's going to require some custom solution where, again, you're relying on the client to control when that high-speed process starts, stops, and then a way to receive buffers of data. How do I configure OPC-UA to connect to a cloud server? So I've personally never tried this, but it should be similar to how you would connect using, say, UA Expert, what was shown in the video, where you need to specify an endpoint, and most likely you would select encrypted connection since you're connecting to a cloud server. You want to make sure your data is safe. I know Azure Cloud from Microsoft does support OPC-UA. Microsoft actually helped to add a lot of different protocols and did a lot of work on OPC-UA. So their configuration should be at least somewhat straightforward. Another question, can I have a control loop running and use OPC-UA? Yes, I think that question is, can I run a control loop with OPC-UA? And yes, you certainly can. Specifically for our hardware, the max loop rate you can run will be dependent on the number of channels that you need Again, 2 kilohertz is a safe bet, but we may be able to run faster in some instances. Okay, why has OPC-UA become so popular? What makes it more attractive than, say, Modbus? Well, there's a lot for OPC-UA. One certainly is the auto discovery, because again, Modbus requires so much input to configure each side, whereas OPC-UA, once you've configured your server, your OPC-UA client can automatically discover the address space. But there's also several other reasons for why OPC-UA is becoming more and more prevalent. Certainly openness and interoperability are main points of interest. And even though OPC-UA is a bit newer than Modbus, it's based on OPC, which is considered to be a mature protocol, and it's already had some adoption. OPC-UA also has built-in security. So for those security concerns of joining the IoT world, OPC-UA seems to fit right in. Also scalability, so we can have many servers all connected to clients sharing large amounts of data. If we remember back, Modbus is simply a definition of how communication occurs and what the bits represent. OPC-UA defines methods, communication definitions, and much more. So hopefully that answers your question there. If not, feel free to contact us. We're happy to answer your questions. And I don't see any more questions. So if that's it, thank you for attending, and I'll let Bob Finn take it back over.
Okay, this concludes today's presentation. A big thanks to Austin and everyone who participated in today's webinar. We'll be continuing the UEI Masterclass at the same time next Thursday. Next week, we'll be taking a deep dive into using LabVIEW with UEI data acquisition systems. Another thing to note, we record every webinar and post the video online. You can watch any of our previous sessions, including this one, either on our YouTube page or on our own webpage, ueidaq.com/videos. And finally, we hope you found today's webinar useful and hope to see you again next week. If you need any additional support or you've got suggestions for a future webinar topic, please email us at support@ueidaq.com or call us at 508-921-4600. And thank you again for joining us. And as always, please stay healthy.